Hello people, it's Zach again today. So this video is probably going to be a little bit shorter one than my last one. It's going to be about Boltzmann's constant and how it's not a fundamental constant of nature. Those of you who are familiar with the ideal gas law, which it should be pretty much anyone who's taken an introductory physics class, know that it's like PV equals nRT, P pressure, V volume, N is the number of moles of your gas, R is what they call the universal gas constant, and T is the temperature in Kelvin. Now this R value, what this universal gas constant is defined as Avogadro's number times the Boltzmann constant. And so when you have the number of moles times Avogadro's number, what that gives you is the total number of molecules, which we normally write as big N instead of the little small n. And so you can actually rewrite the original ideal gas law as PV equals NKT, where the N is capital instead of lowercase, and it indicates the number of molecules in the gas. So this leaves us with one more thing, which is like, what is this K? What is this Boltzmann's constant? So those of you who are familiar with the kinetic theory of gases, which is a little bit higher level, are probably familiar with like the idea of what pressure actually is in according to that theory, which is that it's these gas particles that are moving around inside of your container or whatever. They exert forces on the inside surfaces of the container when they impact with it. And because there's 3 different degrees of freedom within this 3-dimensional space, you can kind of work out like how much force each individual particle exerts on the box, and then like consider that 1/3 of the forces in 1/3 of the molecules in the direction are moving along one particular axis. And from all of this, you can calculate that like the kinetic energy, like the total kinetic energy of all of the particles in the box is equal to 3/2 times kT. Now I want you to consider the fact that this K value is actually a scalar. If you're familiar with like linear algebra or like linear transformations or anything like that, like a scalar, if you say, for example, you have like a distance is like that far, right? And if I was to multiply this by a scalar of 2, what that means is I'm doubling its distance, right? So you can think of this K as being like a scalar for the T. And we're probably thinking like, well, why do we need a scalar for this T? Why is each axis 1/2 kT? Well, consider, for example, our temperature scale, Kelvin. Now, the Kelvin scale is actually the exact same scale as the Celsius scale. It's just shifted down by 273 degrees, so that 0 sits at absolute 0, because the original Celsius scale is defined such that 0 degrees Celsius is the freezing point of water at standard pressure and temperature, I think, and 100 degrees Celsius is the boiling point of water. So what this means is that a temperature difference in Celsius of 1 degree Celsius is actually 1/100th of the temperature difference between the freezing and boiling point of water. So think about how arbitrary that actually is. So really what this Boltzmann constant is doing is that it's taking this arbitrary metric that we've decided, like this, where we've decided our units of temperature are equal to 1/100th of the temperature difference between the boiling and freezing point of water, and scaling that up to a more natural temperature scale. And so if we consider that as only being a scalar, like imagine if we created a new unit of temperature. We're going to call this the Kelvin or something. I don't know. And the Kelvin is actually defined to be this Boltzmann constant multiplied by the temperature in Kelvin. So what this actually does is it just rescales everything, so we have natural units. And so now what ends up being the case is that the kinetic energy for all of the particles inside the box is just this 3/2 T. There's no K in there. And the ideal gas law is just PV equals NT. There's no constant there, because the constant was only necessary because of the fact that we chose an arbitrary scaling metric for our Celsius scale. For measuring our temperatures. So, yeah, it's as simple as that. It's not fundamental. Thank you for watching.